Log on, tune in, find out. Another good idea from Cambridge.
I'm fine.
Okay, so we start a new course that Markus is going to talk about. He's going to give Ringel-Algebras and applications to moduli.
Thank you very much. So let me start with an attempt and a motivation. Okay, so the general setup is we have an abelian category, and we want to study moduli spaces for isomorphism classes of objects in this. So this is only motivation. This is not precise. I don't claim that there exists moduli spaces of objects for arbitrary abelian categories, whatever. But well, we fix some discrete invariants D, like in the vector bundle on curve case, rank and degree. And we have some notion of stability. And then we have some moduli of stables up to isomorphisms. Or later on, we will also consider variants of such moduli spaces, or variants thereof. One typical variant is to consider moduli of polystable representations, polystable objects up to isomorphisms, or consider objects together with some additional structure, like writing as a quotient of something, or the variants of moduli spaces you might know from the vector bundle case. And then the point I want to make, this is the point, I want to make, there exists a certain non-commutative algebra and this is the Hall algebra, H of A, which encodes quantitative information about these moduli spaces. Information on these moduli spaces, where quantitative information means something like Betti numbers, Euler characteristic, or number of points over finite fields, some really quantitative computing some invariants of these moduli spaces. There might be other invariants than counting points or Betti numbers, like what about Hodge numbers, virtual Poincare polynomials. All these directions can be explored. So there's a non-commutative algebra which surprisingly encodes quantitative information about these moduli spaces. It somehow knows Betti numbers of these moduli spaces. The only problem is to answer the right questions to this algebra to get this information out of the algebra. Yeah? It knows about the Betti numbers, but you have to ask the right question for this whole algebra to answer. Okay, so well, okay, that's the next point. So in which situations does this work? So here, there's here and there's there. Here we will consider A an abelian category of homological dimension at most 1, which means that all higher x vanish, of cohomological dimension less than or equal to 1. And there are two main examples. The one which I will not talk about is coherent sheaves on a smooth projective curve. And the other is representations of a quiver. That's the one I will talk about, and I will explain in a minute why. And then all this strategy was also successful there. And this is two rather famous long papers, Joyce Song and Koncewicz-Stoibelmann. Where they do this and lots of other things in the situation where A is a Calabi-Yau3 category. Well, Joyce Song for an abelian Calabi-Yau3 category, Koncewicz-Stoibelmann even for an triangulated, or A infinity, or whatever Calabi-Yau 3 category. But that's a completely different story. We will concentrate on this, and in fact, I will not talk about coherent sheaves on smooth projective curves, but only talk about representations of curves. Why? Well, first of all, in talking about representations of curves, we'll just do linear algebra. So we'll do linear algebra and highly decorate it with an abelian category, with moduli spaces, with a non-commutative algebra. But the essence is all linear algebra. So that's very simple. So that's only linear algebra. And the advantage of concentrating on this case is that all the basic qualitative information on the moduli spaces, qualitative information meaning things like, is the moduli space connected, irreducible? What is the dimension of the moduli space? All these basic geometric facts, all of them are absolutely clear in this representations of curve case because we are just doing linear algebra. Yeah? So the basic properties are already there. And then we can go on and concentrate on quantitative information, actually computing invariance of moduli spaces. Yeah? But this is somehow not disturbed by any complications of the basic setup. Yeah? So I will try to convince you that this is something interesting to look at. And if after the first part you are not convinced, then please pretend that this is interesting, because otherwise these talks will be boring for you. And if I can't convince you, then the following might help you. Whenever I write down a representation of a quiver, which I will usually call V, just replace it by E, coherent sheaf on a smooth projective surface, and all the basic properties will go through because we are just dealing with abelian categories of cohomological dimension less than or equal 1. Okay, so the series of talks will not be an introduction to Joyce, Song, or Kontsevich-Stoiberman. Yeah, it's something like a playground. So this is somehow, maybe for some of us, this is real life, and this is the playground. And on playground, things are simpler, but all the essential features of real life are already there. Yeah? But I prefer to stay on the playground. Yeah? So you might view this as, well, the essence of the techniques of these papers will be in here, but then you have to decorate it by all the technical struggles of the 3 Calabi-Yau situation. Yeah? So that was my attempt at a motivation, and just somehow as a teaser for things to come.
Are these ones in the here area in fact Calabi-Yau 3 categories in some way that's not obvious?
No. In this quiver world, you can produce Calabi-Yau 3 categories from the quiver world by considering quivers with superpotentials and all this part of the story. Yeah? But I will not go into this. I will really stick to the cohomological dimension less than or equal 1 situation. Okay. So just as a teaser for things to come, classical thing in moduli of bundles on smooth projective curves is the Harder-Narasimhan recursion. And the Harder-Narasimhan recursion we will boil down to just one identity in this Hall algebra, which is 1 equals the product over all mu, 1 mu. So that will be the essence of the Harder-Narasimhan recursion. This is something the algebra knows, and then you have to ask the right question, and it tells you all the Betti numbers of the moduli spaces. Yeah? So this holds in this Hall algebra, and this gives the Harder-Narasimhan recursion for Betti numbers in the co-prime case. Okay, that was the motivation. So, quivers and their representations. And now I wonder how much I have to tell you about this. Everything? The whole story? Or, yes, okay. One yes is enough. Okay, so again, I want to motivate this. The definition of quivers and their representations and their moduli by considering some very classical examples of moduli spaces or of GIT quotients. Yeah? And some of these you have already seen in the series of talks by Bernd Doren. So one classical action of a reductive group on some affine space for which you want to have a quotient is the action of general linear group on D by D matrices via conjugation. This is one of the usual first examples when you work out some GIT quotients. Okay, and this is well known. We can make things more complicated, and then things become fun, by considering the action of G on several matrices via simultaneous conjugation. And then the quotients become really interesting and really unknown. So this is some of my favorite example, in fact. Second example is you can consider arbitrary rectangular matrices. You have an action of GLD cross GLE on matrices by row and column operations. And then it's not so interesting to look at this quotient, but again, we can consider tuples of such maps. So the action is via base change. This is just linear algebra, yeah? Producing interesting GIT quotients out of linear algebra setups. Another linear algebra setup is to consider the action of, say, PGLD on points in projective space or on linear subspaces of projective space. Say on m tuples of points in projective space. This is also one of the very classical GIT examples, where it's interesting to work out the quotients and interesting to work out cohomology of the quotients. Okay, and quiver representations are unified language for such problems. So these are interesting. Let's pretend they are interesting problems for GIT and for moduli theory. For example, this situation regularly pops up when you deal with, say, vector bundles on P2. Yeah? There are lots of questions can be reduced to studying this action. This simultaneous conjugations of tuples of matrices pops up in moduli of vector bundles on curves if you do in some local or infinitesimal studies. So there are, in fact, close connections of these problems to moduli of vector bundles, but we'll just treat it as interesting problems in themselves because it corresponds to unsolved problems of linear algebra. Yeah? So there's no normal form for tuples of matrices up to conjugation. This is an unsolved problem. Okay, so I hope this motivates the following definition of what a quiver is and what representations of the quivers are. So quiver, Q, is, and for this series of talks, all the quivers which appear will be finite, is an oriented graph. So that's a quiver. So quiver is some more colorful word for oriented graph. Okay, and to encode the structure precisely, we need a set of vertices, I, and a set of arrows. And these arrows I'll write as alpha from I to j, indicating one arrow from the vertex I to the vertex j. Examples? Well, the examples which we'll see in a minute correspond to these three examples are the following. So first of all, let's keep it simple. One vertex, a single vertex, and then a bunch of loops attached to it. Because in this definition, nothing prevents me from choosing these arrows to go from I to I itself, and in fact several of them. So it's just a bunch of M loops. That's a quiver. Next example is more complicated, 2 vertices and several arrows in one direction, namely M arrows. Or another example would be several vertices pointing to one central vertex, and again the number of such arrows is M. And now we'll somehow define a notion of representation of quiver such that these problems above correspond precisely to the problem of classifying representations of the quiver. And that's it. So that was the first part of the definition. What is a quiver? I need one more notion. Let's call the quiver. No, I don't know. I have to define this. OK, so what is a representation? So let me work over the complex numbers most of the time. Later on, we will need everything for a finite field. So at the moment, we can just say K should be a field. And then we want to define K representations of the quiver Q. K representation of Q, K representation V of Q is. So it consists of vector spaces, one vector space for each vertex, and linear maps, one linear map for each arrow. So this is always a finite dimensional K vector space. And this is always a K linear map. So quiver representation is just a certain configuration of vector spaces and linear maps. That's what we are dealing with in these examples. Yeah? In the second example, it's somehow absolutely clear. An M tuple of D by E matrices is nothing else than, well, it's a tuple of linear maps in such a configuration, linear maps between the same 2 vector spaces. What is a quiver representation? In this example, we just fix one vector space, and we consider a bunch of endomorphisms of this vector space. That's the first example of the square matrices. And the third example is some more special case of representations of this. What is representation of this quiver? You have a vector space here. You have vector spaces U1 up to UM here, and linear maps from the UI to V. And then we will see later on, for this situation, we can these assume to be subspaces, and in fact, subspaces of dimension 1. And one-dimensional subspaces just means points in the projective space. OK. So we need more than a notion of representation. We want to have an abelian category of homological dimension 1. So we have to define morphisms. So morphism F between 2 quiver representations is the following. Again, it's a tuple of linear maps between the vector spaces which are involved. So one linear map for each vertex with one condition. All diagrams should commute, such that all diagrams commute. That means the following. So what are these diagrams which have to commute? Well, OK, so here we have the quiver representation V. Here we have the quiver representation W. Part of the structural data of V is a linear map V alpha between the vector spaces Vi and Vj. Part of the structural data of W is a linear map Wi to Wj, called W alpha. the datum of a morphism means that I have a linear map Fi here and a linear map Fj here. And now I have a square diagram, and I want it to commute. That's the notion of morphism between representations of a curve. Okay. So fact, and then we'll work out some examples. That defines an abelian category. Oh, of course, we need composition of morphisms, but that's obvious. We just compose them for each vertex I. Yeah? This defines a category, and in fact, an abelian category rep Q, representations of Q, and if I want to specify the base field, call it rep KQ. And this is, in fact, an abelian subcategory, and it's a finite length category because the vector spaces involved are finite dimensional. So all objects have finite length because they have some finite dimension. Yeah? You cannot produce infinite filtrations, descending filtration. This defines an abelian category of representations. And OK, so in an abelian category, in particular, we have a notion of sub-object and isomorphism. Just to see if we understand this concept, let's work out what are sub-representations and what are isomorphisms. So sub-representation means that we have an object which is a sub-object, so all the morphisms should be injective. So we just have inclusions. Sub-representation is nothing else than a bunch of subspaces in the given vector spaces Vi, which are compatible with all the structural maps, such that V alpha maps Ui into Uj for all arrows alpha from I to j. And what is the notion of isomorphism? So if we have isomorphic curve representations, then in particular the vector spaces they are living on are isomorphic. These are finite dimensional vector spaces. We consider them up to isomorphism. So let's just assume they are K2 something. Yeah? So let's assume that V is given by the vector spaces, some vector spaces K to the di, and linear maps, V alpha from K to the di to K to the dj. And these we can represent as matrices. Yeah? So now we're getting into a really concrete linear algebra situation. So curve representation up to isomorphism is just a bunch of vector spaces K to the di and matrices A alpha. So this is a dj cross di matrix over the field, because it's a linear map from di-dimensional to dj-dimensional space. And choose another one on the same vector space with matrices B alpha. Then what does it mean for these representations to be isomorphic? It just means that these matrices you get out of these matrices by base change in all the vector spaces. So these two are isomorphic if and only if the collection of the matrices B alpha arises from the collection of the matrices A alpha by simultaneous base change in all the vector spaces which are involved. Okay, so I will give a precise formula. So what does it mean that they arise via base change? That means there exists automorphisms GI, such that you get the B alpha as base change from A alpha. That means you perform base change in the vector space k to the di, and vector space in the and base change in the vector space k to the dj. Yeah? And this should hold for all alpha. Okay.
So for all alpha, the GI and GJ are fixed.
So for all alpha, okay, for all alpha, which is an arrow from I to j. Yeah. So examples. Yeah. Let's do some examples. So let's take as a very easy example the quiver with a single vertex and a single loop. Because then all these indexing by arrows and vertices is not necessary because there's just one vertex and one arrow. Yeah? So everything should be really simple in this case. So what is a representation? It's nothing else than a vector space together with an endomorphism phi. Yeah? We need a vector space for each vertex and a linear map between the vector spaces for each arrow. Okay, so what is a subobject? A subobject is then a subspace of U which is compatible with the structural map, which means a subspace which is preserved by this endomorphism. For example, an eigenspace or a generalized eigenspace. So what is the notion of isomorphism? So up to isomorphism, we can replace V by k to the d. And then this endomorphism is nothing else than a square matrix. So our standard situation is k to the d, and here we have a square matrix A. And then A and B give isomorphic quiver representations if and only if we can reach B from A via base change with a GI in the source of the arrow and GJ in the target of the arrow. And because source and target coincide, this means that B should be GA G inverse. So we are just dealing with matrices up to conjugation. In particular, this means that we have a classification of all the isomorphism classes in this abelian category. It's just, say, over the complex numbers, it's a Jordan canonical form. So that's pure linear algebra. Second example. And of course, well, OK, now what happens if we take several loops here? So taking several loops means taking several endomorphisms phi and considering them up to simultaneous base change. And that's more difficult. OK, second example is this quiver, just one arrow between two different vertices. What is a representation? We have two vector spaces, V and W, and a linear map F. A subobject means choosing a subspace here, such that F maps the first into the second. What is the notion of isomorphism? Up to isomorphism, we can assume these vector spaces are k to the d and k to the e, and then F is just given by a matrix. And then we are considering matrices up to base change both in the source and the target space. So A isomorphic to B, if and only if there exist invertible matrices G and A, such that B equals H A G inverse. In first year linear algebra terms, we're considering matrices up to row and column operations. And what is the optimal normal form for that? Well, identity matrix of size R by R, where R is the rank, and the rest is 0. So again, linear algebra tells us classifies the objects in this abelian category for us. Yeah? So here we have 3 discrete invariants up to isomorphism, namely the dimension of V, the dimension of W, and the rank of the linear map. Yeah? So this is the case where this abelian category up to isomorphism has a discrete classification in terms of 3 discrete invariants. Already in this case, we see that we have continuous invariants, namely the eigenvalues, and some discrete invariants, the sizes of the Jordan blocks. So here we have continuous invariants. These are the eigenvalues. And the discrete invariants are the sizes of Jordan blocks. Okay, one final example to exhaust these 3 motivating examples is the following. Let's consider the quiver with 4 arrows pointing to one central vertex. And now let's keep things very special and just assume that here we have 2-dimensional space and here we have 1-dimensional spaces. And let's classify such representations up to isomorphism, but not all of them, but only generically. Generically, such a representation is isomorphic to what? So that means we have maps from 1 to 2-dimensional spaces. So it's just vectors of length 2, 4 vectors. And we are allowed to apply base change here, which just multiplies the vector by some scalar multiple, and base change here, which multiplies the vector by some invertible 2x2 matrix. So what happens generically? Generically, the first is non-zero, so we can, without loss of generality, assume it's 1, 0. Assume that the second, generically the second is linear independent of that, so we can normalize it to 0, 1. Then, what can we do with a third vector? Well, it shouldn't be, generically, you can transform it to 1, 1, and then you are considering the final 4th vector, lambda mu, just up to scalar multiples. So we get a continuous invariant in P1, and that's just the cross ratio of 4 points. Generically, such a representation is isomorphic to this form, and this just corresponds to the cross ratio of 4 points in P1. And this is nothing else than taking semi-stable configurations of 4 points in P1 and modding out by the PGL2 action. Yeah? So this connects to the third case of considering tuples of points in projective space. Okay. So these are examples of representations of quivers and of these categories. And now we see that in some cases we have a complete overview over all the isomorphism classes in the category. And in some cases we don't have, namely if we have lots of loops or lots of arrows. And so there's a lot of theory about in which cases you can classify all the representations. For example, this phenomenon, I don't want to go into this because that's some of the orthogonal story to all this moduli space story. You might ask, for which quivers do you only have discrete invariants? Well, this holds by a theorem of Gabriel if and only the quiver, considered as an undirected graph, is a disjoint union of Dynkin types ADE appearing in Lie theory. Yeah? So you have only discrete invariants if and only if the corresponding unoriented graph is a disjoint union of ADE Dynkin diagrams. You have continuous invariants, but mostly harmless continuous invariants, namely not more complicated than eigenvalues, if and only if the quiver is a disjoint union of extended Dynkin diagrams, A tilde, D tilde, E tilde, appearing in classification of, say, affine Kac-Moody algebras, and so on and so on. And so there's lots of connections to Lie theory. All this we will skip, because we are interested in the situations where there is no known classification of all the isomorphism classes, where we have to consider moduli spaces. Yeah? So in this case, where you only have discrete invariants, all moduli spaces will reduce to single points. In the case where you have invariants as complicated as the Jordan canonical form, all moduli spaces will restrict to P1 or Pn. Yeah? And we'll consider the rest where you have interesting moduli spaces. Wow. Okay. That was lots and lots of very elementary examples, but I hope it's helpful for motivating the following. So now, after these examples, let me collect 2 or 3 basic facts on this abelian category of representations, which shows that it is somehow a parallel world to coherent sheaves on a smooth projective curve. So some facts on this category of representations. So first of all, this category of representations is in fact equivalent to the category of modules over a certain algebra, a certain non-commutative algebra. This has nothing to do with the non-commutative algebra H, the Hall algebra. Yeah? So this is something completely different. This is something called the path algebra of the quiver. So it has a linear basis consisting of path in the quiver, and multiplication is concatenation of path. And then it's not so difficult to write down this equivalence, which means in particular that everything you know about categories of modules also works for representations of quivers. Okay, so what about the Grothendieck group of this category? And now, yeah, to be on the safe side, let's assume complex representations. No, for what we really want to have, that's not necessary. So it's somewhat similar to the situation you have learned about yesterday in Daniel Heubrecht's talk, that usually this Grothendieck group is huge, infinitely generated. You want to approximate it by something discrete, by some finite dimensional thing. And this can be done here too. Namely, we have a natural map to what was called gamma yesterday, the numerical version of the Grothendieck group. So the Grothendieck group, again, is defined by considering isomorphism classes of representations and mod out by exact sequences. We have an abelian category, so we have short exact sequences. And if you mod out by short exact sequence, then the following map is well defined. You map V to its dimension vector. What is the dimension vector? Well, recall what V is. It's just a collection of vector spaces, one vector space for each vertex. And at each vertex, you can take the dimension. So take the dimension, k dimension, of the vector spaces Vi, and collect them all together. And this is then an element of the free abelian group generated by I, and that's called the dimension vector of the representation. And this is a well-defined map, because if you have an exact sequence, well, like consider modules, yeah? If you have an exact sequence, then the dimensions add up to the middle term. Yeah? So this is a well-defined map. And this is our replacement for the Grothendieck group in the general case. So I should formulate some exercises so that there's something to do in the tutorials. So first exercise is, this is an isomorphism if Q has no oriented cycles. If Q has no oriented cycles, because then I claim that the only, okay, so let me give you one hint for this exercise. We're considering all representations up to short exact sequences. So this is then freely generated by irreducible representations, representations which have no subobject. Yeah? And in the case where the quiver has no oriented cycles, there are only finitely many such irreducible representations, namely the irreducible representation Si, which looks as follows. Put a one-dimensional vector space at the vertex I, and everything else in this quiver representation is 0. All the vector spaces, all the maps are 0. That's an irreducible representation. You cannot think of any non-trivial subobject. But in the case where the quiver has no oriented cycles, these are the only irreducible representations. Yeah? And then this map is an isomorphism. So at this point, I should be careful about terminology. So usually what I now called an irreducible object, usually people in representation theory call a simple object. But in the context of vector bundles, simple often means trivial endomorphism ring, right? And this is somehow a bit confusing. Simple in representation theory just means no subobject. And this notion of trivial endomorphism rings in representation theory is called Schurian, because these are the representations which look like in Schur's lemma. Yeah? So I will use the terminology irreducible representation. So these are the only reducible representations. Okay. So next two facts is that this is a category of homological dimension at most 1. All the higher x vanish identically. And even more important than this, well, if all higher x vanishes, then we have something like an Euler characteristic by taking dimension of Hom minus dimension of x1. Yeah? This is then an Euler characteristic. And there is an explicit formula for this. The dimension of Hom minus the dimension of 1. Well, because all higher x vanish and all negative x vanish anyway, because this is modules over some ring, then this is an Euler characteristic, which means it's well defined on the Grothendieck group, and it's even well defined on this numerical factor of the Grothendieck group. It's given by the so-called Euler form. So this is a form, bilinear form, which only depends on the dimension vectors. And now I have to tell you what this cute bracket means. Bracket DE, this Euler form, is defined as sum over all the vertices di times ei minus sum over all the arrows from I to j di ej. Okay, so these two homological facts can be seen quite easily by exhibiting some standard projective resolution for all quiver representations. Yeah? The projective representations are known, and then in fact there is a certain kind of standard resolution which you can just write down, check that it is a resolution, and look at the long exact sequences, and then you're done. This was known since 1976.
Do you have some schedules?
Haha, yes. There's something like seriality. This is the Auslander-Rayton translation. And then you can really get something like x1 of VW is isomorphic to Hom W, the so-called Auslander-Rayton transpose dual, except for, well, there's a little anomaly if V and W are projective or injective representations. But yeah, there is something like seriality. Yeah. I haven't defined it. It's Well, there are several ways to define this. In this quiver case, I always mix up the right, which direction to go. You take the dual space of homomorphisms of V to the dual of the path algebra. Or is it X1? I will check, but yeah. Basically, there's a Serre duality in here. Okay, I will check the precise formula after the talk. I mean, the usual definition of this tau is pretty lengthy and complicated, but has the advantage that you can directly get this formula. There's a very short formula for which it is difficult to derive Serre duality. So, okay. So this is the homological Euler form. And, well, if you want some more really simple exercises, why not, I mean, if you really want to understand all these concepts, then why not take this case here? Then we have a good classification of all the representations, just given by 3 discrete invariants. And just for the fun of it, work out all the dimensions of HOMs and dimensions of X. Yeah? Dimension of HOM you can do explicitly in terms of these invariants. Dimension of X you can in terms of this. So second exercise, work out all HOM and X spaces for representations of this quiver with just a single arrow.
Do we need to know what injective or projective objects are?
Sorry?
Do we need to know what injective or projective objects are?
No, we can work out the HOM directly, and then we can work out the X from this formula for the Euler form. Yeah, and then after we know what the X is, we can see if we can find well, in fact, the X1 we'll really realize by equivalence classes of short exact sequences. This we'll really do tomorrow. And so there's no need to know about the projective effect. Okay. Should I stop in time, or do I have these 10 extra minutes? Yeah? Okay, great. Then I can start with the moduli spaces. Okay. So now we have abelian categories which really behave like vector bundles on a curve, or coherent sheaves on a smooth projective curve. And we can imitate all the necessary definitions to define moduli spaces. So second part, moduli of representations. We need a stability. In contrast to the case of vector bundles on curves, there is absolutely no canonical stability for representations of quivers. Yeah, there are, well, in this case of the quiver with just 2 vertices, you can show that there's only one reasonable stability, in fact, but in general, there's absolutely no canonical choice of stability. Yeah? So in the vector bundle case, we need rank and degree. The rank has an analog. That's the, say, total dimension of the representation. Sum up the dimensions of all the vector spaces. That's the rank. But there's no analog of the degree. Absolutely no analog. So we have to make a choice. Choose. And everything will depend on this choice, in particular the fact whether the moduli spaces will be non-empty or not. Choose theta, which is just a functional on the Grothendieck group, or in fact on our numerical version of the Grothendieck group. So just some additive function. And how does such an additive function look like? Well, theta of d is nothing else than take the sum of our vertices, theta I times di. And that's our replacement for the degree. Well, once we have this, theta, we can define a slope function. Slope function mu. And now this works now only for non-negative integer combinations, linear combinations, and produces a rational. The slope of a dimension mu is defined as the fraction of theta applied to d divided by the replacement for the rank, which is total dimension of d. total dimension of D, and I have to define this. Total dimension of D is just the sum of all the entries Di. And non-negativity and excluding 0 ensures that this denominator is non-zero. This is the replacement for the rank, and this is the replacement for the degree, which is artificial from the very beginning, because there's nothing like the degree. But that's a slope function. And now you have slope of a representation. If V is a non-zero representation of the quiver, then you define its slope as the slope of its dimension vector. Okay, and now you define semi-stable, stable, and polystable as usual, with the slope condition for subobjects. So X is semi-stable, stable, polystable, if and only if, well, semi-stable means the slope weakly decreases on proper non-zero subobjects. Stable means the slope strictly decreases. And polystable means it's isomorphic to a direct sum of stables of the same slope. XV. V is isomorphic to a direct sum of stables of the same slope. Okay, that's canonical. And also all the basic facts which you know about stability and semi-stability, they are really universal to all abelian categories. So once we have an abelian category, such a numerical slope function, we know that we have the usual behavior of the slope in a short exact sequence. Yeah? We know that all the semi-stables of a fixed slope define an abelian subcategory. This was also mentioned yesterday. So we have all usual properties of semi-stables, which we all know and like. Like if we consider the full subcategory of representations V, which are semi-stable of slope of a fixed slope mu, then this is an abelian subcategory. So we can really work just inside this category, consider kernels, images, co-kernels, extensions, direct sums, sub-objects, whatever. And also we know that we have the Harder-Narasimhan infiltration, which is unique. So precisely like in the setup yesterday. So, and so on and so on. So all the basic properties of stability go through. The only question is whether we produce anything interesting, because everything depends on the choice of this theta. Okay, now we have all the ingredients there, and we can finally define the moduli spaces. And this is the last blackboard I will clean. Oh, yeah, important exercise, very important exercise. So I made clear that in general, this choice of the stability condition is a very subtle one. It might produce nothing interesting. So there's one case where there's a canonical choice of theta. So first of all, if the quiver has just one vertex, show that all stabilities are equivalent to the zero stability. Being equivalent means stability and semi-stability for this are the same as for this. Yeah? That means equivalence. So equivalence means yielding the same semi-stable objects. And that's the interesting case. If the quiver has two vertices, then there are only three stabilities, namely the stability given by the functional 0, 0, 1, 0, 0, 1, and 1, 0. So this is the, yeah, they're all equivalent to one of these. And these two are not interesting. You can work out what the stables and semi-stables are. There are just few of them, and that one is interesting. And that's the notion of stability which, in fact, appears in several papers. Drese studied these under the name of Kronecker moduli. They also appear as one of the main examples in Ellingsrud-Strömme's calculation of cohomology of quotient, cohomology rings of quotients. So this is interesting. That's the exercise. Okay, so now construction of the moduli spaces. And then we are finished for today. And then tomorrow I can first give a list of the basic qualitative properties of the moduli spaces, because that's easy from the construction. And then we define the Hall algebra. So construction of moduli. Goes as follows. We want to define moduli space for theta polystable representations of dimension vector D. So how do we do this? We just want to apply GIT. We consider the following space. Well, first of all, we need a space where all the quiver representations of dimension vector D live. That's easy, because if we fix the dimension vector, that's still on the blackboard. If we fix the dimension vector, then all we have to do is to choose matrices. Yeah? So let's just take the direct sum over all arrows of the space of di cross dj matrices, say now of the complex numbers. That's the parameter space for all the quiver representations of dimension vector D, because the vector spaces can be assumed to be k to the c to the di. Yeah? So a point in here is just a quiver representation. The notion of isomorphism is then just this action of simultaneous space change, this formula. And this formula means that we have an action of a certain group on here, and this group is take the product over all I and I, GL of c to the di. So that's the base change group. A point in here is just a collection of invertible matrices GI, acting on these matrices with precisely this formula. So we have an action of a reductive algebraic group on a vector space, and then we want to form the quotient. Yeah? But we want to form the quotient with respect to semi-stable points. And so that's basically the definition. But now we have to work out that this notion of semi-stability is precisely the notion of semi-stability you need for doing GIT, meaning that some semi-invariant function doesn't vanish. And in fact, this is true. So this quotient is nothing else than the approach of the following. You take the coordinate ring of that space, and you consider functions which are semi-invariants with respect to this group, semi-invariants with respect to some character chi and powers of that character. Yeah? So the usual approach construction of quotients, and I have to tell you what this chi is. Chi should depend on theta. And chi theta, so that's a character on our group, product over GLs. to the multiplicative group. So we know what the characters on GL are, just powers of the determinant. So characters on products of GL are just products of powers of determinants. And now we just have to choose the right power. So in principle, we want to take something like, so in principle, we would like to take that one, but that's wrong. Let me explain why. Yeah, so that would somehow be the basic idea. That should be the choice of character. But this is wrong for the following reason. You can embed the scalars diagonally into this group. Yeah, and then the scalars act trivially via base change. Yeah? If you just plug in a scalar matrix lambda here and here, then they just cancel. So the scalars diagonally embedded act trivially. And this we should keep into account when defining this character. Yeah? And so we have to modify this character. There's a choice of signs, which is important. We have to modify this character to, apply theta to D minus total dimension of D times theta I. So that's the right choice of character. Because now if you plug in a scalar matrix, let's check what happens with a scalar. No, I promise not to need more than one blackboard. Okay. Exercise. Work out what happens if we plug in a scalar matrix. Then the determinant of that scalar matrix is lambda to the dimension di. And then if you take this di times theta d minus dim d theta I of d, then this gives 0. This exponent is 0, so the character vanishes on the scalar matrices as it should. Yeah? And then you take the approach of the graded ring of semi-invariants with respect to powers of that fixed character. And that's the usual approach construction. And then Alistair King showed by somehow working out what the Hilbert-Mumford criterion means in that case, that on such a representation, you have a non-vanishing semi-invariant, if and only if this representation is semi-stable here. Yeah? So it's really direct application of Hilbert-Mumford in this special situation. OK, so that's the moduli spaces we'll start with tomorrow. Thank you very much.